Well, okay, we are taking a look at the mechanism here. Now I've changed and made a motorized version of the previously hand cranked one. I found these planetary geared motors that can run at a sufficiently slow speed. So here's what it looks like here when it's running. Right, and you can see I've got my velocity and acceleration vector arrows on top of that. So here it is in real life, and I have put the motor in place. They're kind of interesting. I've been looking for something along these lines that was affordable. I had previously, in other attempts, used gears to run down with the thing. Let's see, does this one run? No, I guess probably the batteries are probably dead. Let's see if I can make the thing move out of the way. No, I got to get that out of the way to make it go. Okay, so you could see what I had to do, and one of my obstacles for having students do that was didn't have a very good supply of these. I had to buy these gears together, and to able to and then, like 3 worm gears came with each collection of like 50 gears. I wasn't able to find those by themselves, and I couldn't 3D print them out well enough. They also had a little problem of sticking right in there, but this really did a big amount of the reduction. But this little motor goes like 15,000 RPM. I mean, it's crazy how fast that thing goes. You could reduce the voltage a little bit, but this was already low voltage. This was 2 AA batteries, which I think only comes out to like 3 volts. So that didn't work very well, and it wasn't a good option. Here's another one that I had done with the same thing. So this is a much better option right here, and I got like these for $38. I got 10 of them for $38, so $3.80 each. But I couldn't find them on like an individual basis, so that's kind of a good thing that we were able to find this. So hopefully I'll buy a bunch more later on. I also have some battery boxes coming for the time being. I just happen to have a 9-volt connection right here. So we're going to half-ass it. One thing that you'll note already is that I'm having some issues with the tolerance. What I did was to take one of the gears from SolidWorks here, and then I had to put it in. Let's see if it's going to open up. There you go. So you can, by the way, you have to remember that you can't like open up SolidWorks gear by itself, really. You have to put it in from the toolbox into an assembly. All right, so this is just a sub-assembly, and then I made this little cap piece right here, and then mated it up with the gear, and then can you want to get there? Go to there? It doesn't want to. All right, well then, hell, I'll just close you, and then you have to see it, don't you? So anyway, when it came to, well, I could probably point this out in a lot more detail if I took it apart. It was difficult to, put this thing through the back of the mechanism and have it come out just the right spot. Have the motor shaft just come out to the right spot. So I have it protruding enough so that this hole gets pretty damn close to line up, right? In order to do that, though, and then all I'm using is a little paper clip. I need to find a better pin to put into there that's closer to the diameter, because I believe that's causing a certain, because you can't make the planetary gear go backwards, by the way. I mean, you can't drive the planetary gear with this side of the thing. It's just too hard to do. So that right there is slack. If you could kind of see that the shaft isn't really moving, That's not very good. That's a lot of slack going on right in there. We don't really want that. So I need to already we could see that this is a little bit of a problem, I think, and that's a lot. So because I don't want to bother taking that out right now, and I just want to show this thing in motion, just give you an idea of the speed, that this is like an appropriate speed. And as I mentioned in an email and probably in the project, you could also take maybe a potentiometer, aka a pot, like a tar volume pot, or so you get a linear. That's an audio taper. You could probably get a linear taper, might work better for trying to control the speed of this. So we just want to reduce the voltage. Oh, and what happened here? How come it's not going? Huh? Is it stuck? Oh, I know what happened. All right, so it is stuck. I'm having a little bit of a trouble. This wasn't a problem before, but it is now. And I think it might be that this Teflon nut, the Teflon's no longer being working correctly. So I could take it out. Yeah, you can tell that it's really tight right now. Okay. So what these Teflon nuts do, and you can see that I have this arrangement so that this captures the nut, right? And then, let's see if can I push it out? Yeah, I can get it out. Okay. So, yeah, it's probably I probably worn the Teflon down by way of here. So I have that in there so it doesn't like tighten as it turns, but it was tightening as it turned, and that's why that happened. So I have to go through my big old box of stuff and find a new nut, and hopefully that will fix the problem, although I don't really see the Teflon in that. So this makes for a great video. There's a lot of design aspects to this that I think was made for an interesting thing, kind of like a course I would want to take. That's what I was aiming for with this course. Because when I first taught it at the Coast Guard Academy, substituting for a professor who's on sabbatical, I was like, geez, I wish I had taken it. All right, so actually this one too is getting tighter. I could feel that right there. Like it tightens up as it turns, but it's still free. Like you also have the problem it could loosen up too, depending on what direction it's going. That's the whole idea behind the Teflon ones, that we could try to solve that problem. Because in reality, you would not make a machine that would, that would not be good engineering practice to be designing a machine that relies that uses a bolt as a shaft. But let's see, I'll get this started. And what I generally do is I tighten it up all the way and then back off on it, especially when you're first doing it, because the nut will seat inside this thing. You want to get it seated, and then you back off from it. And I think that's going to be okay. Well, there's a little bit of a learning curve in there. So one thing that can help this is trying to avoid the friction between these two parts. You'll see that I put in these little metal washers, and that does seem to help. I can also include some nylon or are they Teflon? I don't know what they are. Washers. In the packaging, and maybe I'll do that. Anyway, I think this will go back into play, and then I can do a better showing of what it does. Hopefully, it won't get all tightened up again. And the battery box would have been preferable to doing this, because now I can't, and I would solder the thing up too if I had a switch. So the battery box has a switch on it, so you don't have to keep doing this. All right, so this is a pretty good example of how fast the piece is doing. You kind of see there's a little bit of slack here because it's lagging. And it might be, you could just reverse the wires to make it go the other direction. But yeah. So some of the other features to pay attention to. And I'm going to make an E-drawing out of this, and maybe I'll display what that looks like, because not everybody is familiar with the E-drawing. And let me open this up. I don't know why it's doing that. Let's see. It's going to get mad there. Sure. And so what we could do for an E-drawing is you go to Publish to E-drawings, and amongst the options, it saves the Save Motion Studies. Okay, so we'll just do the E-drawing, and I think it'll wait a little while before it makes E-drawing, so we can keep talking. Oh, there it comes up. Onto my other screen. There you go. So here's the E-drawing of this piece, and you can hit things like animate, and it'll just start looking at the different views of it. Oh, that's really nice. If I had made an explosion view, I think it would have exploded it. No, it did it on its own. There you go. So what you could do now is you could see the different features within here, including how I have done a little bit of trickiness to attempt to keep the motor in the correct place. Oh, I forgot. I meant to buy some little tiny, I think these are M2 screws, but I haven't done it. Maybe I'll make that and try to include that in in the list of stuff, because I don't think they're that expensive. Probably like $10 for like 100 of them or something. But anyway, they could screw into place, and that'll definitely secure this motor, because right now I'm relying on that flat place right there, and I've left a little bit of a tolerance. Anytime you're doing a 3D printing thing, you have to remember that the printing actually is usually like a bead of about a point. Is it 0.2 millimeters? So actually 0.1 millimeter goes onto either side and reduces the size of holes and that kind of thing, generally speaking. So you want to kind of check for that. But anyway, that was my means. So these little motors, let's see if we can go back onto here. They have little threaded holes right here that are pretty sure are M2s. Let's see if I go to here. I think I'll upload this as well. This thing of the motors. You could kind of see this has a description of the motor and dimensions. So you could you could look at these for constructing your the way that you want to make this. This is not the only way to make this. This is just my first pass at trying to have a thing that will make the motor come through. But if you were to, let's say, I guess we can't drag this around. When I was alluding to the fact that I was trying to make this thing thin enough that this shaft's stuck through far enough so that it would make sense for where this hole went and connected to there, right there. So that was the point I was trying to make. Hopefully that makes a little bit more sense to the construction of this. But this E-drawing will definitely help you with the dimensions that I chose. Once again, like this is the SolidWorks one, but the actual one, when after it gets 3D printed, is different. So when you go to choose the depth or the dimensions, you could go ahead and benefit from my experience here. I decided that I wanted to print this thing flat. So this is one of my design decisions, was to make for 3D printing, make it easier if I didn't have a foot right here on the front. But I was afraid that this thing would like topple over this way, because there's a lot more, if you look right here in this direction, there's a lot more weight on this side than there is on the back side, except for that motor. So I figured, you know, I didn't want it to lean this way. I was also a little concerned that it would kind of go diagonally right there, because this thing is flopping around and can make it, but it seems to be okay. So other features that you can might note yourself is I decided to make this little rim around the thing, and it also uses, you know, I could just make it completely thick, but that uses a lot of PLA usually. I have rubber cemented this guy onto the bottom. He's so he'll stay in place. I'm pretty satisfied with some of those design decisions, but you could make your own. Some of the most important ones are the crossing of the pieces, right? You will see that I made this thing up high enough that it can pass over this piece right there. But I also wasn't sure, right? And you know, that I needed to offset a little bit because these guys were getting really close and interfering. So I put a washer in between there. I probably could have put another washer to lift this up high enough, but by putting one right here and right there, this was able to have enough clearance to pass over that because these cross, right? So those sort of design decisions that I had to make. I made this gear thinner than that gear so that this piece right here could pass over the gear. I've also put the gear right here just to get this out of the way of that. You'll recall maybe from if you did gear design, this is actually an idler gear and serves no purpose in terms of the gear ratio. All it does is it moves the centers over. And in the design of the driving dyad, I ended up, going outside of maybe where the box, maybe this box right here was from the original problem out of Norton, and I decided to extend it back up over here. That's totally legitimate. By the way, this portion of the thing is going to be different for everyone. You can make different decisions. Amongst the usefulness of this, if I can make this thing move, and otherwise I would just take out that because I kind of like this, but I should find a larger pin to put through there. As you're going through here, this is an excellent example of the transmission angle or a bad transmission angle. But this, fortunately enough, this motor has a whole lot of torque. It's a good amount. So anyway, let's rotate this about here just a little bit more, and then pay attention to the transmission angle. I'll just pinch them on there. Maybe I should have got alligator clips. That's what I should have done, but I didn't. So there's that. Oh, look, you can see my beard in there. So you can see as it gets down there, as it gets down right to there at the bottom, that's not the greatest transmission angle, right? That would be if you extended this, that would be the transmission angle that's in between there. And think about it having to lift this up. Like this is the only direction the force can go. So it's trying to lift up a thing that's all the way down over there. That's a tough ask, but obviously it's possible to do. So that's sort of the idea of the transmission angle, right? In this case, it's the lift up that's the difficult one. You can also go the other way around. And got it wrong. Let's see. Come on. I'm trying to pinch. I'm not looking. That's why. Yeah, I should put alligator clips, but that's all right. I'm gonna have the battery boxes gonna show up tomorrow at my house. Yeah. So anyway, this is going to be a cool project, I think. And we're going to do some analytical synthesis on this. to generate these spots. Basically, we're trying to find the location of those 2 points, and mathematically. I'm going to introduce the vector loop concepts on here, and solve those equations for position. And we're going to get the velocity and acceleration, and approach those and then compare those to the velocity and acceleration that you get from here. So like you can, so results, we can take a look at plot. Let's see, plot, we could go show plot right there. So here, here's velocity. And so you can see the velocity at that point right here. And I just chose that spot. And see, we can see that as it goes through different positions right there. You could see, yeah. And then the same thing with this acceleration. You could show the acceleration plot of that point, what it should be. But now that we have we will have a physical piece, we could also put like take a permanent marker and make a little dot right here, and use this tracker program and take a video of this, and also, analyze the speed. Actually, the speed of this, I guess, is what we'll take a look at the speed of the input of the thing and compare it to the output, and we can compare it to what we have right here. So we could actually probably adjust this to match what the real one is going to be and compare these. We won't be able to measure, well, maybe, no, I probably won't be able to measure the amps that are coming out of that, and then try to go back, because we have the voltage, right? We can measure the voltage and the amp, so we can figure out how much torque, with the RPM, we can figure out how much torque is going through there, because we can find how much power with the current and the voltage, because you can go to a motor, any motor like this right here, and you could go to this right here, and you could pull down, and you could find the force. Okay, the momentum, energy, and power. So you can find the torque as one of the things we might want to find. So we have the where'd you go? Losing it. Translational angular momentum, kinetic energy. Oh, so it must have been the force. Yeah, forces. There you go. We can find out what the motor torque is going to be. And I believe it's about the z-axis, because it doesn't show me where my axes are anymore. Let's see. Can we go back to the other one? It doesn't want to, because we're in the middle of this. But I think that's going to be the z direction if I have made this thing correctly, because I think that's x and upwards y. But we could create, let's see, this right there. Boom. All right, so here's the torque as a function of time. Of course, you can't read this scale right there, but here is the torque that's happening onto the motor as you're going along. And because we have, we can see the time history of this, we can get sort of a sense of which direction the torque is going to go, right? Some of them are going to be negative. That's interesting. I think I put the motor onto here, so it's not actually the motor onto here. Right. So anyway, this is a long video, but I figured it would give you some ideas for writing stuff in the paper. Right. We want to write a paper that's going to describe, not a step-by-step, how-to manual, but do some deep diving analysis, mechanism design analysis, and some takeaways, like thoughts that you have. Look up other papers that are, listed. Probably Google Scholar is a good place to start, and looking at other mechanisms that might be applicable. Find some stuff, teach yourself some stuff, some things about mechanisms and related to this process, and write an interesting paper that people want to read. So that is the end of the video.